Good morning, everyone. It's great to have you here for another webinar. This week we have Richard Bowman talking about thermal comfort, ways to design for performance, assessment and compliance, and how to use dynamic thermal modeling to mitigate against overheating. I'm just going to go over some housekeeping before we get started. Please keep your mics on mute. If you have any questions, pop them in the chat box. The webinar is being recorded and will be popped on MESHWORK afterwards. As you all know, we're working really hard to develop MESHWORK into a collaborative environment. We encourage all of our members to learn from one another, share ideas and push sustainable design forward. We're covering the circular economy next month with some really great speakers. We've got Duncan Baker-Brown, we've got Darren Gray, and Talene, who worked on the ACAN Circular Economy series. They're all going to be speakers along with a few others. So make sure you join those webinars because they're going to be really interesting. But for those of you who aren't familiar with what Mesh Energy do, we are an independent and holistic energy consultancy. We're based in Surrey, but work on projects all across the UK and the globe. Primarily, we work with design teams and architects to make the sustainable design process as simple and as cost-effective as possible. But that's enough from me. I will now pass over to Richard so he can get going with his webinar.
Thanks, Catherine. Morning, everybody. Today I'm going to provide an introduction to overheating, how it comes about and how we design for future thermal comfort. And this is crucial to understand as heat stress related mortality rates are expected to increase with climate change over the next 80 years. And so really we need to design for the future as buildings today, as they'll still be in use in 80 to 100 years' time. So what is thermal comfort? Well, broadly, thermal comfort is where there is a broad satisfaction with the thermal environment, i.e. it's neither too hot nor too cold. And thermal discomfort occurs where it's either too hot or too cold, but will not make occupants unwell. Thermal stress, on the other hand, is where the environment will cause clearly defined, potentially harmful medical conditions. And this may include dehydration, heat exhaustion, or on the other end of the scale, frostbite. And respiratory problems can also occur. Thermal discomfort can cause fatigue and irritability, and it can increase risk and as well as a fall in productivity. There are many factors to take into account, but thermal comfort is fundamentally about how we interact with our thermal environment. Are you feeling too hot or too cold, or is the space drafty or stuffy? And so fundamentally, thermal comfort is to do with the heat transfer of the human body and the quality of air in the indoor or outdoor space surrounding us. So the four main factors are temperature, humidity, air movement, and air quality. And like natural daylight and overheating, they're symbiotic. Now, at the same time, we are also metabolizing food to give us energy, and this arises mainly in the form of heat. And this can range from 60 to 480 watts, with normal office work generating about 140 watts of heat output from a human body in the form of what we call sensible and latent gain. And latent gain is where heat changes state. And so heat is lost from the body by evaporation, radiation, convection, and conduction in order to maintain a normal core temperature of about 37 degrees C. And if we get too hot or too cold, then, well, if we get too cold, for example, then the core temperature sort of retracts inside the body to protect those essential organs. Of the four, conduction is the most negligible, so we can actually discount it entirely. But evaporation takes place through the breathing and sweating if necessary, with radiation and convection taking place through the skin and sometimes respiration as well. So from the body, normal heat loss is about 25% evaporation, 45% radiation, and 30% through convection. But in a well-insulated building, this will shift slightly. So evaporation will fall, whereas radiation, convection heat loss or heat emissions will be around about 30%, 38% each. Now, in terms of the surrounding environment, air temperature affects the degree of evaporation and convection. Relative humidity, which is the moisture content of the air, affects evaporation only, while the mean radiant temperatures affect radiation from the body. And the mean radiant temperature is the temperature of the surrounding space. And at the same time, air velocity in a space affects evaporation and convection. Now, although evaporation is always a loss, we gain and lose heat by radiation and convection. Hence, hot and humid conditions reduce the means of heat transfer away from the body. And so as designers, we're most concerned with the operative temperature, which is a combination of the average temperature and the average radiant temperature of the space. Relative humidity, on the other hand, is a percentage ratio of the amount of moisture in the air at a particular condition, so a particular temperature, compared to the maximum amount of moisture in the air at the same temperature that the same temperature and pressure can hold. And so what that means is 0% relative humidity is completely dry, and 100% relative humidity is fully saturated, at which point we notice moisture in the air and start to get condensation. Typically, warm air holds more moisture at a higher pressure, and equally, warming air will cause a fall in humidity. Now, although humidity doesn't affect feelings of warmth, it does affect perceived air quality, and is therefore associated with overheating. For example, with relative humidity below 25%, this can cause eyes and skin to feel dry, while greater than 80%, we start to feel sticky and uncomfortable. And so we're really aiming for a relative humidity of about 40 to 70%. Now, air movement, as I said earlier, causes a cooling effect, but this is why we don't always appreciate drafts, depending on the time of year. And so airspeed in the occupied zone needs to be low, but air supplied at a higher level can be mixed before entering the occupied zone, and therefore we get that balance of comfort. And generally, the range of comfortable indoor air velocities are typically about 0.1 to 0.3 meters per second. So it's actually very low. Now, on the screen in front of us, this is a psychometric chart, and this chart illustrates the relationship between the dry bulb temperature and the relative humidity. Now, the dry bulb temperature is the temperature of the air without being exposed to the sun. And so what we can see on this graph is really the top of the curve, if you like, is where there's 100% humidity. And that's anywhere between -5 and so about 20 degrees C. And then we have a whole range of different humidities depending on the temperature. So the real outliers there are, we've got, let's see, about 35 degrees, then humidity is dropping to about 25%. And this is the weather file for Gatwick Airport. And so we're aiming to design spaces that fall within the comfort zone. And this comfort zone is typically between sort of 18 and 28 degrees, and a relative humidity of sort of around 40 to 70, as I said earlier. So it's quite, and given that in the whole scale of things, it's actually quite a narrow sort of comfort zone to actually get a building to fall into. Other factors that affect our sense of overheating is too much temperature variation in the space, air and radiant temperature differences, too much localized radiation, say from radiators or stoves or other heat emitters that give point heat emissions, and mitigating localized discomfort by keeping floor surfaces to about 19 to 29 degrees. So when we're in contact with the floor, we don't feel discomfort either. Complementary to this is the provision of fresh air, and fresh air really is to provide oxygen for respiration, to dilute carbon dioxide produced as a byproduct of respiration, to also dilute contaminants produced as part of occupation, such as odors and VOCs and so on, and to give a feeling of freshness in the space. And to achieve this requires about a fresh air supply of about 0.2 litres per second per person to provide oxygen. We need about 1 litre per second per person to dilute CO2 in the space. And we need about 5 litres per second per person to dilute occupational contaminants. But to give a feeling of freshness requires 10 litres per second per person. And therefore, we require about 50 times more fresh air to both dilute odors and create an acceptable fresh feeling than we do just to provide the oxygen we need. However, this does vary according to building and room types. And for this, we always refer to CIBSE Guide A, typically table 1.5, which gives a range of building types and conditions, target conditions. And this covers everything from industrial, health, hotels, leisure, offices, places of public assembly, education, and sports halls and so on, amongst others. And research over the past 100 years has shown that social factors and psychological responses also affect thermal comfort. For example, in World War II, submarine crews were effectively guinea pigs for immediate studies as to the effect of heat buildup, thermal stress, stale air, and so on. And what's happened is many comfort indexes have been developed since then. But because we're all different, the predicted mean vote is considered the most reliable. And PMV, as its acronym, measures the comfort of a large group of people and is typically used to assess condition space. And you'll also see this in BREEAM HEA 04 credits requirements if you're working on a BREEAM project. Now, Fanger carried out lab research to establish this PMV, but also it established what is known as the predicted percentage dissatisfied, also known as PPD. And this is to predict acceptable comfort conditions. And PPD is effectively a function of PMV. This is all written down in standards such as BSEN ISO 7730. And is also referred to by ASHRAE 55 and also CEN standard BSEN 15251, which also underpins the Energy Performance of Buildings Directive, which is used in building performance assessments. So PMV was found to correspond with thermal comfort sensation studies. And these were carried out between 1975 and 2002, mainly by Humphreys and Nicol. And their field studies asked building occupants about their feelings of comfort to understand how comfort expectations varied with different climate and internal conditions. And so really what we're looking for is a predicted mean vote of around plus or minus 0.5. And this correlates with a dissatisfaction of less than 10% for and a thermal sensation ranging from slightly cool to slightly warm. But then again, if you look at 0, this equates to neutral and 5% dissatisfaction. There is a CBE online tool that allows designers to explore the impact of PMV and adaptive methods, which I'll come to in a minute, for occupants' thermal comfort ASHRAE 55. And it's a great way to explore the relationship between spatial variables. So it's worth looking that up and having a play. It's from Berkeley Labs in California, who are great at giving out free building performance tools. As I said earlier, while it's statistically impossible for everyone to feel comfortable all the time, people can adapt. And this is what we know as adaptive thermal comfort. And what that means is that people, it's recognized that people can adjust their metabolic rate by how active they are, changing their clothing levels. For example, winter clo level internal temperatures are sort of expected to be about 22 to 25 degrees C. but summer CLO level internal temperatures of 25 to 26 degrees C will typically satisfy predicted mean vote requirements. We can also take warm or cool drinks. We can modify our local environment, but also we can change the environment as well. And so thermal discomfort occurs when temperatures typically change too fast for adaptation to take place. They're outside the normal limits of comfort, they're unexpected, or they're outside our individual control. And this adaptive approach to thermal comfort indicates that higher internal temperatures may be generally acceptable. So during warm summer weather, 25 degrees C is taken to be the acceptable summer indoor operative temperature. Whereas between about 25 and 28 degrees C, occupants may feel hot and uncomfortable. But above 28 degrees C, this will lead to dissatisfaction for the majority of occupants. And designing for performance, we've got a number of guides that are available to us. CIBSE Guide B, section 2 really refers to ventilation and air conditioning. And this is considering the strategic choices facing the heating system designer, including the requirements imposed by the intended use of the building, energy and environmental targets, legal requirements, and other possible interaction with other building services. And this is succeeded by a definition of requirements and calculation of system loads, characteristics, and selection of systems, components, equipment, and fuels, followed by commissioning and handover. So it's a very comprehensive guide for M&E engineers. But this should now be used in conjunction with CIBSE TM65 for establishing the embodied carbon in building services. And this was only released this year. It's also CIBSE Guide L for sustainability, and section 8 is devoted to health and well-being. And then CIBSE AM10 is almost the equivalent of CIBSE Guide B, but it's concerned with natural ventilation in non-domestic buildings. But it works in a not too dissimilar manner as CIBSE Guide B in its structure. And then we have different methods for assessing different types of building. The first one is CIBSE TM52, and this is for avoiding overheating in non-domestic buildings, and this refers to BSEN 15251. And really, there's three criteria set. Criteria 1 sets a limit for the number of hours the operative temperature can exceed the threshold comfort temperature by 1 Kelvin between the beginning of May and the end of September. Criteria 2 is about limiting the severity of overheating in one day, while criteria 3 really sets an absolute maximum daily temperature, beyond which normal adaptive measures are insufficient. And this criteria really covers the extremes of hot weather conditions and future climate scenarios. And typically we need to satisfy criteria 1 and 3 to pass TM52, as criteria 2 is a little bit harder to predict. And this is assessed by using a dynamic thermal model set up against the project room data sheets for time of use of regulated and unregulated heat loads and occupancy, solar thermal gains, window opening, and so on. BB 101 from 2018 is the guideline for naturally ventilated thermal comfort and indoor air quality in new and existing schools. But the overheating risk assessment is carried out for specific hours of 9 till 4, with a lunch break between 12 p.m. and 1 p.m. Monday to Friday, from the beginning of May to the end of September. So it's similar to criterion 1 of 252, but not quite. And the summer holiday period is included as if the school was normally occupied, as schools are now becoming community hubs, if you like, for summer clubs and so on. But unlike TM52, criteria 1 must be passed, while criteria 2 and 3 are for information only. But BB 101 also includes stipulations with regard to stack and mechanical and hybrid ventilation, along with the positioning of intakes and exhausts, as well as managing polluted exhaust from labs or cooking spaces, air quality, filtration, and purification. CIBSE TM59 is the design methodology for the assessment of overheating risk in homes. And this allows really for comparison between different designs. And criteria A and B apply to naturally ventilated dwellings. So criteria A is effectively the same as criteria 1 for TM52. But criteria B is really assessing the operative temperature of bedrooms at night to guarantee a good quality night's sleep. However, the design criteria for dwellings predominantly mechanically ventilated by MVHR, for example, is a little different. When employing MVHR, the maximum temperature is set for all rooms for the whole year. And designs still have to be assessed using a dynamic thermal model. But TM59 sets generic heat gains from time of use of unregulated loads and occupancy levels according to the number of single or double bedrooms and whether a kitchen, living, dining space is open plan or whether they're separate spaces. When you're considering apartment blocks, there are additional profiles for communal corridors, service voids with and without service runs, and cupboards that might have heat interface units fed by a district heat network. So up until now, we've been looking at design for performance. And then there is also, as you're all familiar with, design for compliance through building regulations Part F for ventilation. And this stipulates the minimum litres per second supply and extract flow rates or air changes per hour and whole building ventilation rates that vary depending on use and fabric first air tightness. And this is designed to inform the supply rates to dwellings, spaces, and extract rates from sanitary and cooking spaces, while other spaces act as buffers. And suffice to say, what is taken out, what is extracted, must be supplied back into a building to create circularity of airflow. However, in my experience, design for performance generally leads to compliance. And therefore, we're looking for occupant thermal comfort and then satisfying building regulations. If you don't have it, this is a book worth having on your desk because fundamentally, we're seeking to manage solar thermal gain through passive design to avoid overheating. And this is not to be confused with passive house methodology. So in the summer, this means reducing solar thermal gain while admitting daylight and maintaining views out. But conversely, in the winter, this means admitting solar thermal gain to reduce energy consumption while mitigating glare, maintaining views out, but also reducing heat loss. And so it's important to bear in mind the location of glazing areas on the facade, as well as the openable area of the glazing, as both govern passive solar thermal gain and the flow of air. But also the relationship between the position of thermal mass and insulation also plays an important role. And at the end of the day, overheating is part of the fabric first approach in reducing energy demand. This image is a recent project we're working on. And so what we do at MESH is we explore the impact of measures such as atria, fixed shading devices, whether that be overhangs or fixed vertical or horizontal brise soleil, in conjunction with natural or mechanical ventilation strategies. And really the purpose is to design out the need for energy consuming, CO2 emission increasing space heating and air conditioning as far as possible. And so we can simulate the lowering of internal and external blinds, louvers and shutters, but not the leaves on the trees. That's a common question. But unfortunately, the software is not that good yet. But equally, it is important to be mindful of the building form and orientation, the position of the building in the landscape, and the relationship to green infrastructure such as shelter belts, as well as the topography, as this all affects the flow of air through a building. So a good place is to start is to benchmark the existing glazing design and specification and window opening strategy against current and future weather UK CIP climate scenarios. And we're not just interested in the U value, we're also interested in the G value of the glass to understand the heat transfer through the glass. And G values have an important role to play in the admittance of solar thermal gains and their positioning on different facades. So typically we'd have a lower G value on the east, west and south facade and a higher G value on the north facade. And so we carry out overheating analysis against current and future climate scenarios. And these emission scenarios reflect the anticipated atmospheric CO2 parts per million. And this can be anywhere between about 480 to 970. And that's categorized as low, medium and high. When we do overheating analysis, we will start with a 2020 scenario that has high emissions as a worst case scenario. And then for 20 and 50s, we look at medium to high emission scenarios. And then at 2080, there's a low, medium and high scenario. But typically we're looking at medium in the anticipation that actions will be taken to mitigate increases in atmospheric CO2 ppm. And so DSY1 2020 high and DSY2 and 3 for 2050 medium are typical assessment scenarios at this time. We can then assign openable window types, and these are given algorithms that emulate occupants opening windows. Please note that the bedroom windows are deemed to be open sooner to ensure good quality sleep. And there's actually some variance there in when the windows are open and to what temperature as well. And unless there's no mechanical ventilation, then we're expanding those algorithms so that windows are always open based on CO2 levels to alleviate stuffiness. But for domestic projects, bedroom doors are always considered closed at night for privacy. So that has an impact on the cross ventilation and cooling of open window strategy. Of course, the CO2 function is removed if mechanical ventilation and heat recovery is specified, but window opening for cooling remains in place. And of course, the windows are specified as to how they are hung and the openable area. And we derive that information from plan sections and elevations from the architects that we work with. And what this is doing is determining the openable area through which air will flow throughout the season. So, for example, a side hung window will open up the complete rectangular orifice. Whereas if it's a top hung, then really the openable area is a combination of the triangular openable areas to the side of that window plus the rectangle. So the openable area is significantly reduced with top or bottom hung windows. That's worth bearing that in mind. And then what we can do is analyze the relationship between solar gain and operative temperature, but also it's not on this graph, but we can also analyze bulk airflow rates and the impact of shading devices. So what we're seeing on this graph at the moment is if you're looking at the master bedroom, for example, you can see that because it's a predominantly an east-facing room, then we get that immediate solar gain first thing in the morning, and that just tails off throughout the day as the sun rotates around the building. But the initial temperature climbs with that solar gain ever so slightly. But then because of air movement throughout the house and stack effect, then that room will continue to warm gradually throughout the day, albeit not as much as the garden room and the living room in this case. And then we provide these results back to architects and clients. We run multiple iterations to understand how design interventions are actually improving the performance of the building. So the right-hand table in this case is the results for criteria A, while the left-hand table shows the likely range of operative temperature. So you can see there's up until 2040, we've got the studio space, which is compliant in the terms of TM59. But then when we start looking at future climate scenarios, then the percentage of overheating starts to increase to really above 3% most of the time. And therefore, if we're designing a building with longevity, then we'd need to make some more design interventions there to alleviate that problem. And then on the right-hand side, you can see that the minimum temperature is effectively the room set point temperature for the heating system, with a mean temperature, but then it also, the maximum temperatures there range from anywhere between 28 to 37 degrees in the entire period up to 2070. So we know that the severity of overheating is going to increase as well. So what can we take away from all this? Well, really, overheating depends on what we're wearing, for the activity we're doing at the time of year, and whether we're hydrated. Relative humidity and stuffiness and freshness should all be accounted for as well. And different types of space have different comfort requirements. We do know that green and blue infrastructure provide cooling, but we can't account for that in thermal models at this time. But building form and orientation, as well as the extent of glazing, must be carefully shaped to appropriately mitigate solar thermal gains. As glazing is really the source of heat loss and solar thermal gain, and so this needs to be balanced so as not to be a weakness in the design. And also, it's worth bearing in mind that ventilation is not the same as cooling, but openable windows and attenuated ventilation can cool under the right circumstances at the right time of day in the year. And that really brings me to the end of this presentation, a little bit shorter than my usual. I'll hand you back to Catherine for questions.
Thanks, Richard. That was really, really interesting. He covered the last bit of health and wellbeing that we wanted to this month. Does anyone have any questions? Feel free to pop them in the chat box. I only had one that kind of came up through all of it. So I found it quite interesting how you make the assumptions that certain doors will be closed, and that's how you do your thermal modeling. Would you say that a post-occupancy evaluation of homes would make future thermal modeling like better and like be able to improve it more?
Absolutely. I mean, the point of POE really is to, it's a lessons learned activity to understand occupants' subjective appreciations of the space they're in and where they think changes could be made to improve things in the future. But also POE is also designed to collect objective data. So when you're doing a post-occupancy evaluation, you're also installing the likes of data loggers to measure operative temperatures, relative humidity and CO2 levels. And what that means is if you're doing a POE with a view to refurbishing a building, then you can start to calibrate the thermal model to represent what is actually there today. And of course, none of those, the algorithms I presented on the screen, they're not fixed. They're just a good starting point. We do have projects where we've had particular windows specified that can be locked open at night, and therefore they are being used on the ground floor. So we're getting nighttime cooling, and we're sort of going beyond that assumption that ground floor windows are closed at night, and we're only relying on upper floor windows. Okay,
that's really interesting. I don't think there are any more questions. Oh wait, we've got one, Rob Walker. You mentioned that shading for trees can't currently be modeled. Deciduous trees can't be modeled, and they are, and there any workarounds that can be applied now, or any plans for software developers to include this feature in the future?
It would be fantastic, but it would make it an extremely complex piece of software. The reason for that is that a deciduous tree, for example, we know from research that during the summer, when they're in full leaf, then they'll provide about 80% shading for their sort of volume, as it were. But what happens if that flips? So the branches and trunk that are left will provide about 20% shading, but we'll get 80% admittance of sunlight. Unfortunately, all trees are not made equal. and so they will shed their leaves at different times of year, different rates, and so on. But also, unfortunately, they're not a fixed asset, as it were. They can be blown over, chopped down, cut back, and so there's almost too many variables to include. You could, in theory, if you wanted to study the impact for a particular month or day, is to model an external shading device that was representative of the shape of the tree. But this, we wouldn't use this in building performance. It's a strict no-no for us.
Okay, that's really interesting. Yeah, it sounds like there's way too many variables to make that a part of it. Okay, if that's it from everyone today, we'll end the webinar there. But thanks again, Richard. It was very, very valuable. I'm sure people will be watching the recording of this as well.
Okay, great.
Thanks. Bye.
Thanks. Have a good day, everybody.